Here yesterday. I should introduce myself. I'm Michelle Burford. I'll be chairing this session this morning of 3 talks. Our first talk this morning... Yes, you're right. Tim, before I introduce Tim, yes, a very important thing, a pair of men's spectacles were found in the gents. So if anybody's missing a pair, that's where they are. Tim Malthus will be our first speaker this morning, talking about a very topical topic that we've heard a bit about this morning, about sensor observations for cyanobacterial assessment. Thank you, Tim.
Good morning, everyone. So my talk very much complements and follows on from what Mark presented in the keynote this morning. And we have this kind of vision, if we call it that, in CSIRO around the idea where we could develop a complementary set of optical systems for detecting water quality, measuring algal blooms, and that relates from the water sampling. We have a project which is looking at its citizen science and the role of colour that we can get from our mobile technologies, through to surface water sensors, the middle graphic there, which is the thing I want to talk about today, and then on to satellite-derived systems, as Mark has so very eloquently shown. So this is one of 2 talks. I'll present the concept of this near-surface water quality sensor we've developed and the history behind it, and then Philip Ford will follow up in the second talk, showing a really nice application of this approach. So, as Mark introduced, the whole thing that drives this system is essentially that there is information in the spectral reflectance from water bodies, and if we have a sufficient spectral resolution, which is one thing he stressed, we can get quite a lot of information. So this is 4 New South Wales water bodies, the reflectance spectra, varying in productivity, and we can see what we effectively see is the inverse of the absorption spectrum in reflectance. And so we can relate some of those features, in particular, to the presence of pigments in phytoplankton, and we can relate it to chlorophyll concentration and phycocyanin. So we can use some of this information to derive, as Mark showed, useful algorithms, and we can make some estimates of chlorophyll concentrations and the presence of blue-green algae. So we have also, like Mark, developed a satellite-based system for algal alerting for New South Wales. That's the system on the right. So we have a visualisation system, and this is really driven by Landsat and Sentinel data. The reasons why Sentinel-2 data, so higher resolution data than what Mark was showing. And I'll talk about the reasons for that in the next slide, but this just shows one example of the visualisation system we have. Very interestingly, this is also for Lake Hume, and the time sequence there shows a bloom, 2016 bloom, a series of Landsat images taken over Lake Hume during a bloom time during that 2016 Murray River bloom. So when thinking about satellite data, Mark spelled out the advantages of this. It's a really good complementary tool. It's systematic, repeatable, wide coverage. It's brilliant for that. So it helps fill in those gaps that monitoring programs perhaps can't see. But it doesn't fill in all the gaps, as Mark sort of touched on in some ways. So if I can take some of the limitations first, spatial resolution, I'll take that one first. We did an analysis in CSIRO that actually showed the size of water bodies in Australia is much smaller than other continents, and so that actually if you look for 4 contiguous pixels around that sort of Sentinel-3 size, there's only about 10 to 15% of the water bodies across Australia actually fit into that. A lot of our problems, of course, occur in rivers, and this shows a nice example of Sentinel-2 applied to river detection, and we only get a few pixels per little stretch of river reach. I like to call the rivers slow-moving lakes. The rivers in Australia are slow-moving lakes, essentially. But we can actually see chlorophyll detection there. Spectral resolution is also limiting. Compare the spectral bands of Landsat versus Sentinel-2, these medium-resolution sensors, so we still have a limitation. Timeliness is an issue. If we build a system for Australia based on Landsat and Sentinel-2, we only have a sort of 3-day revisit time, whereas Sentinel-3 and Mark's system is daily. The overpasses may still be obscured by clouds, so that's always an ongoing issue. And on the system I showed you, the satellite data, the one challenge we really had was latency. We were relying on the Australian Geoscience Data Cube, now Digital Earth Australia, and the speed with which Geoscience Australia could actually upload the data became a factor in limiting our application in New South Wales. So onto the second tier. So I've long been driven by the sort of passion of having an intermediate step between applying the same principles as satellite remote sensing, but to something above the surface of the water. There are a number of instruments, as we can see on the right, which have actually used in oceanography largely, but they're all very expensive. And so these instruments, in order to make a satisfactory measurement of reflectance above a water surface, you need 3 measurements, and that's what the diagram in the middle shows. You need an estimate of downwelling irradiation, an estimate of radiation from the sky, as well as your measurement of reflectance from the water body itself. The combination of those three measurements gives you a very accurate measure of spectral reflectance. These 3 instruments have 3 spectrometers in them to achieve that goal. And as you can see, they're all very expensive. So I went to some clever people within CSIRO with the idea of can we develop a sensor that's above surface that incorporates these 3 fields of view, that is much cheaper than those systems. Those are very expensive. What we want is we want to have a cheap device, and so we can have more of them. We can use this as a validation tool and a separate measurement tool in its own right. And one of the challenges with these instruments is calibration. Can we remove this need for calibration between those individual spectrometers? So a very clever person by the name of Stephen Gensimer came up with a proposed solution. And I just showed the sort of evolution of this solution through time. This is the very first concept on the left here, a stick. This is what I call the Bunnings version. It's just $20 of plastic pipe from Bunnings and a bit of optical fibre connected to a spectrometer. And hey presto, we could, for a very highly eutrophic ornamental pond in Brisbane, we get really good reflectance spectra generated from this very simple device. From that, we can actually then create a chlorophyll index from lots of measurements we've made. And again, we have sort of thresholded this on alert levels. This was something that Lee Bowling and I developed, the set of green, amber, and red thresholds, as you can see in that diagram, very similar to the ranges that Mark actually presented for his system. The second version of the sensor looked like that. We have 3, 4, 5, and 6 are the optical inputs, and we put some cameras on it, which are 1 and 2, 1 looking up at the sky, and 2 looking at the water surface. And we've installed a couple of those around the system, and they've been working for a while, and I'll show slides on that in just a minute. If we validate the results, so this is a validation in different water bodies around southeast Queensland and around New South Wales, and it's a comparison of a Atlantic underwater spectroradiometer versus our above surface sensor. And you can see there that the correlations are extremely good. The above surface measurement, our cheap sensor is the black line, and the Atlantic sensor, our expensive scientific instrument, is the dashed line. The above surface sensor is not corrected for sun glint, and this explains a lot of the variation that we see in the low wavelength regions that we see in the low wavelength regions. I'll leave it at that. And we've since moved on to actually evolve this instrument even further into what we call Mark III, or what I call Mark III. And this is so the idea of the sensor, if I can go back to this diagram here, is that it's a fixed sensor. So some of these sensors, particularly the Dalek sensor, actually is motorised. It will actually continuously orientate itself to the sun, so it always maintains this viewing geometry that you can see there. Our sensor obviates the need for a solar tracker, and we've fixed it, but what we've done is essentially added on additional fields of view to cope with the path of the sun during the day. So this is the sensor here. It actually has now 8 apertures, and the key thing that makes this system really cheap is that all of these are delivered through the one spectrometer, all of these optical inputs. So it just has one spectrometer inside it, and that's got rid of the need for calibration. So this is an example installation in Lake Jerrabomberra, just outside the ACT, which we've had installed since about April. So it has the sensor itself. It has a solar panel, and underneath the solar panel in the shade is a small control box, which is telemetering the data back. This shows the quality of that Jerrabomberra system. We see the 3 inputs. So there are 8 inputs essentially in that diagram there, and you can see the quality in terms of signal to noise that's produced. The cameras, so we have a sky view camera on the top right, and we have a view of the water itself with the other hemispherical camera that you can see there. And this is really good. Philip will show the power that the camera actually has just in showing a time series. And these instruments are measuring, instrument is measuring every 15 minutes. We've since gone on to develop machine learning methods in terms of, we're looking for rapid ways essentially to estimate water quality. And so with some of our spectral data already, we've been applying a machine learning method to simultaneously derive total suspended sediment, non-algal particulate matter, chlorophyll, and CDOM. And we're working on a blue-green algal index as well. So just a couple of examples in terms of applications. This is the one that Philip will talk about. So we've had one installed at the Melbourne Water Treatment Ponds in Werribee now for about almost a year. This is the system here, so it's this kind of Mark II version, but it's producing fantastic data. And this just shows the sort of richness. So this is just simply for the 14th and 15th of February. It shows some of the richness of the data produced. And because the sensor is producing 15-minute data, you can actually begin to look at changes in features and diurnal sequences, and Philip will talk about this. I'm not going to steal any more of his thunder. He will show some of the really nice things that can be derived from that diurnal sequence of data. We've also been trying them out in aquaculture. So this is an installation, again, of a Mark II sensor in an aquaculture pond in some of CSI Road's experimental prawn ponds on Bribie Island. And you'll see the challenge we have in this situation is where the ponds are actually covered. So we're actually making these measurements under a cover, but still we're getting reliable measurements of spectral reflectance. And from that, the idea is really to use the sensor as part of a sensor network, which is really trying to manage the water quality in the pond, and in particular look for the onset of cyanobacterial blooms such that control measures the ponds can be flushed, so it doesn't actually impact the productivity of the prawns. And this is a very simple linear regression model that's over a series. So each of these samples is at 15-minute intervals and shows some of the goodness of fit that my colleague Joel Dabrowski has managed to achieve with that. So in conclusion then, did we sort of meet the targets in this? Yes, we have a number of, in terms of the key drivers, I don't know why the question marks have appeared there. They were just supposed to be text, but anyway. So the system is above surface, so that reduces the amount of maintenance. That was a key driver. So we don't have the maintenance issues faced by in situ monitoring systems, say, such as fluorometers, the problems of biofouling, etc. Sure, the lenses still need cleaning, but perhaps less periodically than in situ systems. It offers that 3 fields of view, and we've actually built on the number of fields of view we have. It is much cheaper, so it's coming in at about 1/5 of the cost of the cheapest device that we saw. So the WISP sensor was about $50,000. We can produce for less than 1/5 of that cost. So it's much cheaper, and that means we can have more of them. We've removed the need for calibration. All of those optical inputs are running through the one spectrometer. And the other bonus is that we've achieved really through a series of iterations. It's been a bit of a long journey, but trying out different chips and different sensors in it, we've actually finally settled on one that now delivers a really good signal to noise. So we have further installations planned this summer. We're just waiting for the weather to improve to install one on Lake Hume. That's going ahead. It'll be installed on the platform which is just beside the dam wall. We're putting 2 into the Penrith Lakes, into the Warm-Up Lake and to Lake Duralia. That's being undertaken with the Office of Water here, in particular with Helen Keenan. And there are some thinking about some deployments in the southeast Queensland area, and also we're going to lend the Kiwis one, and they will install one in Lake Whenui, the water body that Susie mentioned yesterday. So what we've envisaged here is really a network of such sensors which allow for the early detection. So this is a complementary system to the satellites, to other monitoring systems. So it's really allowing for the early detection of water quality problems. It's overcoming some of those challenges of in situ instruments, but also overcoming some of the challenges that we have with satellite data that we discussed with Mark's presentation. And the key next steps for us are really in building, if we have a bottleneck at the moment, it's the amount of data these things are producing at the moment, and that's getting an established system set up in our IT system to actually process the data coming from these sensors. So we're in the process of establishing some workflows, getting there. But what we envisage, and this is just a kind of mock-up, is actually being able to produce dashboards from this instrument that show these. This is the apparent colour of the water. You see the photos taken by the instrument. You can get a reflected spectrum. We have an estimate of, say, of chlorophyll concentration or of cyanobacterial concentration. We have an alert status. And then we perhaps have a time series to show how that has changed over time. And with that, I'll leave it. I just wish to thank SEQ Water for access to some of their water bodies to test out this sensor. Their cooperation was fantastic. But also this is an old logo, I'm afraid. They've had more restructures than I've had hot dinners. The Office of Water, or the Department of Industry Office of Water. I also wish to thank them for the really, really fruitful collaboration in developing this sensor. Thanks very much.
Thanks very much for keeping to time perfectly. Questions for Tim? Mark.
Thanks, Tim. I think this is a fantastic development and certainly will make validation from satellite far easier, so well done. I just have a question around the sampling frequency and integration time of the sensors, and also I guess you plan to put in cloud and glint processing in your operational chains. How far have you got with that?
Sorry?
Cloud and glint sort of detection.
Yes, yeah. So at the moment, that was the intention for, and particularly having the sky-looking camera, was really to detect clouds, and the next step in some of the analysis is to really determine what impact does cloud cover have on those reflectance spectra. We haven't got to that, so we're simply applying that very simple Mobley type algorithm that is taking into account the sky measurements, so it's accounting for sun glint. We just use the standard 0.028 fudge factor in that. And that we need to test whether does that fudge factor apply under clouds and under blue skies. But the key thing, and perhaps I didn't point out, that this instrument is not designed to be radiometrically perfect. The whole concept is really, and I should really put that into the design factors, it's really driven by spectral shape. You can see it doesn't really matter that you have a radiometrically, so it's measuring absolute light levels with absolute accuracy. The key thing is that a lot of these algorithms, as you're aware, are simply driven by spectral shape. So if we're reproducing the spectral shape of the reflectance of the water body, we can then simply derive the water quality estimates. Yeah. Oh, yeah. I'll pick your brains. Thanks.
Other questions? One at the back there. That looks like Brett.
Hi. Who's laughing already? I didn't even say a joke. Tim, good to see you again.
Yeah.
This is coming from my perspective. When you guys talk about reflectance, I wonder about absorption. So is there a model about like the delta or the change, which is not reflectance, but what's absorbed? Because I know some of the molecules that we're really concerned about absorb UV, they absorb infrared, and I'm talking microcyst and saxitoxin, for example. They absorb these wavelengths, and that's how we detect them in the lab.
Okay.
Is there a differential that you could possibly use for remote imaging? Possibly, if technology caught up with the lab?
You can kind of see if you kind of flip those spectra, what essentially you are seeing is the absorption spectra of the different pigments. There have been a number of papers I'm aware over the sort of long history of people applying curve fitting methods, sort of underlying sort of Gaussian curves, or derivatives is another way that people have used to estimate absorption peaks. That might be a possible avenue of pursuit in this. Happy to talk to you further about it. Yeah. I don't know anything. No, I don't know. I don't know enough myself. That's the problem.
All to
Cool.
move on. So thank you very much, Tim.